Alright, so today we're going to be talking about exponential growth and decay, and we're going to be talking about this through the lens of calculus. And so, let's say we just have this initial value problem where our differential equation is dy over dt is equal to k times y. So the growth at a particular point of time depends solely on the amount of quantity we have. And our initial condition is equal to y is equal to y0 when t is equal to 0. So we've gotten all the information to solve for our original equation, and so let's do that. The first thing we notice is that our differential equation is indeed separable because we can have a function of y by just like pulling y to one side, and then we can have k as like just a random function of t. And so this equation is separable, and so we know how to solve separable differential equations. And so using that knowledge, let's solve it. We can bring dy over y is equal to k times dt, and then we can take the integral of both sides. And the left side, we get ln of absolute value of y. And on the right side, we end up with k times t plus c. Now I want to get y by itself, so I'm going to take the exponent on both sides. So I'm going to raise both. And then, so I'm left with absolute value of y on the left side, and that is equal to e to the power of kt plus c. And through the rules of exponents, we know that this is the same thing as e to the power of c times e to the power of kt. And notice how this e to the power of c is just another constant, since c was a constant anyway. And to make things simpler, I'll just represent this as another constant c0. So I'm getting absolute value of y is equal to c0 times e to the power of kt. Now, I want to get rid of this absolute value, and so one way I can write this is y is equal to plus or minus c0 times e to the kt. Now the plus or minus over here only affects the constant, right? So now I can once again re-express this c0 into another constant c1, and therefore I have y is equal to c1 times e to the power of kt. And now we've gotten y to one side and we've gotten t to the other side, and now all that remains is to solve for this constant with the use of our initial condition. So we know y is equal to y0 when t is equal to 0. So we can plug in those values. So y0 is equal to c1 times e to the power of k times 0. This evaluates just to 1, so we get that's equal to c1 times 1. So y0 is simply equal to c1. And now we have solved for the original equation, and the equation is simply y is equal to y0 times e to the power of kt. So notice how the equation we got is simply an exponential function. And so we've realized that the exponential function is just a function whose differential equation depends, or whose growth basically is like at a particular point, the amount of growth is proportional to the amount at a point, because this is the differential equation we solve for. And some things, interesting things to notice about this function is how it behaves at various values of k. So I'm drawing out this graph. Let's say k is greater than 0. We know our initial point is y0, or that's our y-intercept. That's just through the properties of like exponential functions, and you can confirm it by putting t is equal to 0. If k is greater than 0, then we have exponential growth, right? Through as the positive t increases, we're going to see more and more growth. So this is for k is greater than 0. But if k is less than 0, then we get exponential decay. So the behavior for a function kind of depends on what k looks like, but in both cases we have some exponential properties. Now if k is equal to, wait, actually this should be k is greater than 1 and k is less than 1, my bad. If k is equal to 1, then our value at t is equal to 0, so if k is equal to 1, then we have like a discontinuous function where so if k is equal to, if k equals 1 at t is equal to 0, we have y is equal to y0, and at all other t's we have y is equal to y0 times e to the power of k, which is just 1. So we just have a constant function when k is equal to 1, and that's just a special case. But we'll usually not deal with this case because we don't get the exponential growth or decay property. Now that we have seen and derived the exponential function, one important thing that people worry about with exponential functions is half-life. Half-life just represents when a function evaluates, or when an exponential function evaluates to half of its starting. And by starting, I mean the value at t is equal to 0. So we know an exponential function looks like y is equal to y0 times e to the kt. And basically what we want to find out, or I mean, you can write this as y is equal to y0 times e to the kt or e to the minus kt. It doesn't really matter. You'll see both versions. But at the end of the day, half-life is whatever the value of t. So t when y is equal to 1/2 y0. And so we can solve for this t pretty easily through algebraic methods. And so let's just solve for the general half-life formula. So we have 1/2 y0 is equal to y0 times e to the minus kt. We can cancel out these y0s. We have 1/2 is equal to e to the minus kt. If I take the log on both sides, I get natural log of 1/2 is equal to this natural log of this exponent, which evaluates to minus kt. I can rewrite the left side as minus ln2 is equal to minus kt. Solving for t, I get ln2 divided by k is equal to t. And so now if we're given the half-life of a function, then we can solve for k, and we can easily find the half-life of a function if we also know the value of k. And you get the value of k by the exponential function that determines the growth or decay of a particular application. So that was half-life, and that was exponential growth and decay. Before I end, I just want to do like one other sort of application-based problem that really hones in this idea. And so let's just work on it. Given that force is equal to mass times acceleration, and force is and you can rewrite this as mass times dv over dt. We're given that friction is a force proportional to current velocity. And so we're given that information. And so with this given information and with this given information, find velocity as a function of time. So this might not seem like much information, but now we have all the information required to find the equation of velocity. Because we're given friction as a force, so it's governed by this physics identity, and it's a force proportional to the current velocity. So if I replace this F with some constant k times v, I know that is equal to m times dv over dt. And now if I take this m to one side, oh, and also one thing I forgot to mention is friction is a negative force. So this negative force, because it's acting against your current like if you're traveling in one way, friction is acting on the other way, so you're getting slowed down. So because it's a negative force, this should be negative k times v. But now like we can take mass to one side and we get minus k times v divided by m is equal to dv over dt. And then now, once again, this looks very similar to the first the differential equation we used when we solved or when we proved what exponential functions look like, right? Because I can rewrite this whole equation as minus k divided by m, which is just some constant a times velocity. And velocity was like y, which we saw earlier, and that was equal to dv over dt. And we already know that if we solve for this differential equation, we will get something like v is equal to v0 times e to the minus k over m times t, because k over m is a, and we know that that's like how it looks like. But if you want to just rederive it for practice, feel free to do so. But this is the equation we'll end up with, and this is basically what the question is asking for, to find v as a function of time, and we have done so here. And so you kind of see how solving the initial value problem was very related to deriving the exponential function, and hopefully this made sense.